Good afternoon, dear friends. My name is Taylan Bali. I will be your teacher during this term. So we are starting our course, Mathematics for Social Sciences, and this is our introductory session. So welcome to everybody and have a nice term. As I said, my name is Taylan Zafer Bali. My cell phone is +90 535 726 8372. My email is thailand.baldi@ankara.edu.tr, ankara.edu.tr, and my YouTube channel is Taylan Zafer Bali, my whole name in uppercase letters. And we have also WhatsApp and Telegram groups and channels for the equivalent of this course in Turkish. AU SPF Mat 1-2, but I guess we will be establishing another group for this course in English, the Mathematics for Social Sciences. So you can call me up whenever you really need me. You can email me, but I prefer you to reach me through my cell phone or WhatsApp or Telegram, which I use for the same number. So you are welcome to reach me whenever you need. All right. So if you can see this picture, this is a very interesting one, isn't it? Perhaps you have already seen it before, perhaps not. This picture depicts an impossible situation in our universe, in our world. There are people going up, down, here and there, and geometrically and physically this situation is impossible. Yet the author, the painter, has depicted this situation. I wonder whether you know the name of the painter. The name is Escher. He is a Belgian one. And the picture is famous. He has made many pictures of this kind. So I would like you to make a little research about Escher. You can find it in Wikipedia and in other sources as well. He is a famous painter, mathematician painter. And he is famous for depicting these sort of strange, impossible scenes. He has also depicted on the nature, the biology, the human nature, and so on. But all his paintings are intriguing us. They are kind of special, a little bit odd, and it induces us to think, to reflect about these pictures. Very nice pictures, though. Escher. All right. So here starts our session 0. Salute to all participants. As you have noticed, I started by saluting you, by greeting you. Salute is greet, isn't it? So I started by greeting you, by saluting you. And here the question is, why do we salute? Why should we salute? Is it a simple gesture of kindness or of courtesy, or does it have some deeper meanings? Well, I can just imagine. You can ask now, what does it have to do? I mean, what all this has to do with the mathematics? But we are coming to that, and the saluting is essential. In the primitive tribal salute, the warriors of these primitive tribes in Africa, in Asia, in perhaps in America, these people from these primitive tribes, when they met each other, they just put themselves in this position. They showed under one of their feet to the person whom they met, putting themselves in this position. Can you imagine why? because this is a position which is the most kind of disequilibrated, which in which you cannot attack your interlocutor, the other person. So you are almost completely defenseless against the other person in this position, meaning that you will not attack him or her, you will not harm him or her. This is the meaning of this salute. So let's see another kind of salute, which we know more. Shaking hands. Why do we shake hands? We are shaking hands even nowadays, don't we? But where does it come from? Why? In which societies people shake hands? Where did it come from, this shaking hands? We could wave hands. We could just make a salute with our heads, with our body, as one does in the Japanese, Chinese cultures. Is it in the Asian cultures? You greet with a head, and in in old Ottoman culture, there was something which we called temenna, which you showed with your head, with your hand, your heart, your face, and your head. So this was also another kind of salute. But there is also a common salute, which is shaking hands. Why? Why do we shake hands? And in which societies it started? Just reflect a little bit about it. Well, perhaps you know it already. Shaking hands it comes from societies where people use sword. Because, I mean, in medieval times, or even before, when people use sword, the sword is used with the right hand. You hold your sword with the right hand. But if you give your right hand to the other person, you mean, I will not take my sword against you. I will not kill you. I will not fight with you. I come with peace. You see, this is very crucial actually. So, therefore, the salute is not only a simple show of courtesy, but a vital action, meaning that you will not harm the other, you will not kill the other. So, people are safe about each other. And when we say in Turkish, for instance, or in Arabic, salam, it means peace. The original meaning of salam, or the salute, it comes from the same root as well. Salut in French, it means, peace. Originally it is peace. I come with peace. And come to me with peace, it means. You see, this is essential. So, what is our fundamental question? Our fundamental question is, what are we doing here? You can say it in other languages. Biz burada ne yapıyoruz? Que faisons-nous ici? Que facciamo qui? Que hacemos aquí? Why are we here? These are, in some languages, the equivalent of what are we doing here. You can add other languages as well. But in all languages, it is important. It is a crucial question, a fundamental question. What are we doing here? So let's analyze this question a little bit. Just analyze it word by word. First, we. What are we doing here? Who are we? Who are you? Who am I? Who are we? There are many answers to this question. You can say we are students, teachers, we are workers, we are human beings, we are beings, we are human beings. We are human beings who are studying such and such matters, subject matters. And we are students of the Political Science Faculty of the University of Ankara, for instance. Or you can even narrow this definition. You can say we are students of the Political Science Faculty of the University of Ankara, the management students, studying mathematics in this course, in the Mathematics for Social Sciences course, for instance. This is an answer. So you should discover who you are, who we are. This we is something to discover. And it changes, of course, according to the situation, according to the society we are in, but there is always a we. And why we and not I? Because the lesson, or whatever we do in general, we do it in a society. We are not alone. So there is always a we. There is also I, of course, but this I gains its meaning in a we, in a society. So we is important. We are in a society, be it a small one. Perhaps you are 2 students and I teacher, so we are a society of a group of 3 people, but it's okay. We are we. And we will be, in fact, we during this course. Whether we are together in this environment or we communicate from a sort of distance, whatever. But we will be we in this course. So, here. So, where is here? What is here? And this has many answers as well. Here can be the universe, the solar system, the planet Earth we are living on rather, and it can be our country, Turkey. It can be the city Ankara, our school, political science faculty, and so on, or a class, or an office room, whatever. But we should again be aware of where we are. This here is important. And for us, this here, the political science faculty of the University of Ankara, is important because it's a school of more than 150 years. It's one of the oldest institutions in the modern Turkey. It started in the Ottoman Empire as the public administration school of the Ottoman Empire, and after the Republic, it became the public administration school of the Republic of Turkey, and we educate also students from other countries. So our main purpose here is to educate people to the public sector or to the private sector or to NGOs, wherever in which sector they can be working. But we intend to educate administrators, managers, be them in the private sector, public sector, or NGOs, or wherever. And it is important because to administer means to take responsibility, your responsibility and the responsibility of the others. So this is important to be an administrator. You should administer yourself, you should administer your family, you should administer your city, your country, whatever, your association, your company. In whatever organization you are, you should take the responsibility and administer. And in our course here, in our lessons, you should take the responsibility of following the lesson and to make the necessary efforts to be successful, be it working, making exercise, and so on. So here, I guess we have an idea about here now. All right, what are we doing here? What? So what is what for you? This again can change from student to student, from person to person. Well, we can say what for someone is to earn money. For another one, it would be to have a good family, to be happy, to work for his country, for the world, for the humanity, or whatever, for oneself. So what changes from person to person? And each one of us should find this what for ourselves. It has not a simple answer. It changes. Also according to the situation, but from person to person as well. And for our course, this what is basically to learn mathematics to acquire some mathematical tools, to learn some mathematical techniques and some essential knowledge of mathematics, in order to be able to think soundly, firmly, and also to use these techniques, these methods, in our profession, be it management or other kinds of administration, whatever we are doing. Probably we will have to use some mathematics, and if we don't have to use mathematics directly, at least the mathematical reasoning, the logic of mathematics, we use it anyway. So, but you should find this what for yourself. Anyone should find for himself or herself. So, and what are we doing here? Doing. Why is it necessary to do? Why is it necessary to do? Doing. Not only being, but doing. So, we are in some place, we are there, in a school, in an office, whatever. And we are in group, in society, but doing something. Why should we do? And the answer comes from an Indian English, well, Indian, but educated in England, a very wise man, a thinker, a philosopher, and a poet, Rabindranath Tagore. So you should also check in the internet who is Rabindranath Tagore if you haven't you haven't read his poems, or if you don't know about him. Rabindranath Tagore is an important personality of the 20th century, especially the beginning of the 20th century. What did he say? He said, you can't cross the sea merely by standing and staring at the water. So you should swim. In Turkish, sadece ayakta durup suya bakarak denizi geçemezsiniz. Exactly. He was a wise man, very wise man. And I strongly suggest you to read the poems of Tagore as well. Very, very, very good poet, very good thinker of 20th century. So in order to cross the sea, we should swim. That means for mathematics, we should use paper and pencil. Without paper and pencil, you can't do mathematics. You can't learn mathematics just by watching some presentations or listening to me or whatever. You should just read the book, follow the presentations, the records, whatever, and then make all by yourself, repeat all by yourself, make the exercises, and so that you can learn mathematics. The only way to learn mathematics is with paper and pencil, paper and pen. Otherwise, it is difficult to learn mathematics. You don't learn just by looking at the table or at the board or at the presentations. Or, well, reading the book helps, but writing and making the exercise by yourself helps more. You should do it. All right. So, well, this reminds me something. A couple of years ago, perhaps 10 years ago, perhaps 5, I don't remember. But, well, in mathematics, there is no Nobel Prize. There is field medal, which is equivalent to the Nobel Prize. In other sciences, even in economics, we have Nobel Prize. But in mathematics, there is field medal, which is another kind of prize. This is the best mathematician prize. A couple of years ago, a young Russian mathematician earned this prize, proving a theorem which hasn't been proven for perhaps 200 years or so. And he was, and he's still alive, I guess, but I don't know whether he works or not. Now he's no more so young, but at that time he was young. So he just went upstairs in his mother's dacha, or in his mother's farmhouse, There was a kind of penthouse over there, a kind of, well, the upstairs, a sort of a calm room, where he went with a bunch of paper and pencils, and nothing else. No computer, no calculators, nothing, no books, nothing. And he just worked there months and months, and afterwards he came with the proof of this theorem, and he won this field medal. And when people, and especially the journalists, asked him, how could you do it? I mean, why didn't you take anything else than paper and pen or paper and pencil? And he answered, well, I couldn't take anything else. There is nothing to do with the computers or calculators, and nobody before me really managed to prove this theorem. So I had the paper, pencils, and my brain. So I used them and I solved the problem. I proved the theorem, he said. You see? So mathematics is done with paper and pencil or pen. All right. So we should swim, so to say, following Rabindranath Tagore, with pencil and paper. All right. And some of the answers to these questions for me, well, those are some for myself, some answer for myself, which I found myself. So you can add others for yourself as well. But here, during this course and during my lectures, what we do in class or be it in a virtual environment like this one, we are curious about the relations in nature, society, science, and mathematics. We are curious. The curiosity is important. Well, one says curiosity kills the cat. This is partly true. But without curiosity, we can't reach anything. We couldn't go to the moon if we weren't curious, if we hadn't been curious. If we hadn't been curious, we couldn't manage to make mathematics or science or anything. Everything starts by curiosity, so we should be curious. We should never lose our curiosity. This is a very important thing, very important talent of the human being curious. All right, so we are curious about the relations in nature, society, science, and mathematics. Besides, we meet young people of all ages. Well, I guess you are young people, but I consider myself as a youngster of 60 years old, something. I passed my 60 years recently. So, but I haven't lost my youth, because youth has nothing to do with the ages. Youth has to do with your curiosity, with your enthusiasm, and with this shining in your eyes. As long as you don't lose your curiosity and the shine in your eyes, you are young. And if you lose them, you can be 15 years old, but you are already old then. The old and young depends on the shine in your eyes and on the curiosity in your brain. This is important. What do we do else? We make an exchange of knowledge, ideas, and culture, of course. If you correspond with me, if you talk to me, if you participate to the classes, to these sessions as well, we can exchange knowledge, ideas, and culture. I learn very much from my students as well. We have very vivid sort of discussions, interactions as well in the classroom, and well, they learn from me, but I learn a lot of things from my students as well. So we exchange knowledge, ideas, and culture. And what is more, we open each other's horizon. This is important because one person is one horizon. If we discuss, if we start communicating, we enlarge our horizons, we see different things, and both people gain out of it. Both people's horizon opens, enlarges, and widens out of it. So this is important. And besides, we prepare ourselves to future. Of course, preparing ourselves to future is the aim of the education. So the main aim of the education is to understand, to cope with the society we are in, and to prepare ourselves to future. And last but not least, we should have a good time. A class or a lecture, a session should not be a torture, but we should have some fun as well in it. We should have a good time as well. And I always have a good time in my classes. I like teaching, and I hope you will enjoy my classes, my sessions as well. So, as well, yeah, this one, this is very interesting. This is something I took from Süleyman Orakçıoğlu. He is the founder and the chief, the president of the Orca Holding Company. This is a company dealing mainly with textiles, as far as I know. I don't know the person, this person personally. I have never met him, but I saw him on TV, and he was explaining his idea of room of aspirations or room of obstacles. This is, he was explaining that this was the key to his success as a president of a holding company. So he says, well, in my mind, I have a room of aspirations, dreams, but some dreams for wishes, actually. Dreaming wishes or wishing dreams, if you wish. Aspiration is this. And a room of obstacles. So I put my dreams, my aspirations, my desires in the room of aspirations, and the obstacles which would hinder me from reaching these aspirations in the room of obstacles in my brain, in my mind. Then I try to annihilate, to erase these obstacles one by one. I make some effort and I erase one obstacle. So I get perhaps one aspiration, one of my desires get fulfilled. Then I try to erase, to annihilate the other obstacle. I work, I make an effort, and I just come over another obstacle. Then I reach another aspiration. So he became the president of this holding company, you see. As managers, I think this is a good lesson for all managers or all people who have some dreams, some aspirations. And of course, there are always obstacles, be it our ignorance or other obstacles, physical obstacles, mental obstacles, whatever. But there is no obstacle which can't be overcome by working, by thinking, by working intelligently. So here is a good sort of lesson from Süleyman Orakçıoğlu. All right. So what is this? What is this? If you were here, we could discuss together what this is about, this picture, this thing. Well, when I discuss this with my students in my classrooms, they say, a tree, a pine tree. Yes, it seems. Somebody says it's an arrow, or kind of several arrows. Well, perhaps, you see, if we see like this, there are some arrows here. We can see arrows as well. You can see a pine tree, a stylized pine tree, or other things. Some people say it's a road sign. I don't know. Perhaps there is also a road sign like this. I don't drive, so I don't know. But yeah, it is a sign anyway. But at the end, I say, well, here there is nothing else than lines and colors. There are some lines and colors. And with these lines and colors, we can represent many things. What do we represent? A pine tree, some arrows, or other thing. All these things, the pine tree, arrow, or road sign, whatever, are interpretations we load over this sign, over this symbol. With these lines and colors, we construct, we build a symbol. This is a symbol. This is a model. You can say this is the model of a pine tree, of a tree. Yeah, I would accept it. This is a symbol of some arrows or some geometric forms. All right, I would accept it, because you can interpret it as you like. One symbol can have many interpretations. One model can have many interpretations. So I wouldn't say no. All right. So when you consider the real tree, it has nothing to do with this. A real tree, if you just look out of the window to a real tree has nothing to do with this, but some stylized shape and color, perhaps. Even the color doesn't match, doesn't fit. I can see trees from my window, out of my window. Here in the court there are some trees. It has nothing to do with this. Even pine trees are different from this. There are some pine trees, they have some slight resemblance perhaps of form, but nothing else. A tree is a complex living being. It gets its water and minerals from the soil, from the earth. It grows. It takes the sunshine. It makes photosynthesis. It produces ATPs, some kind of sugar. It's food, and it nurtures itself with this one, and then nourishes itself with this one and grows. It is a living being like us, a tree. A tree is a very complex living being. This thing doesn't grow, doesn't make photosynthesis, doesn't take water from the earth, nothing. It has some shape and some color. Yet, we use this symbol to represent the tree. If we load over this symbol, over this model, the interpretation of a tree, or we can interpret it in other ways as well. So this is a model. A model is a simple caricature, a very simplified symbol or many symbols describing a very complex reality. So why all these are important? Because in mathematics and in mathematical sciences, be it in physics and economics and whatever, in chemistry, we use mathematical models in one way or another. So and in all sciences and in all arts, we use models. That is, caricatures of the reality, representations of the reality. The reality is so complex that we can't analyze it thoroughly. So we just cut many sort of parts of it, many aspects of it, and we study just one aspect of it with a simple model. This is what we do in all sciences and arts even. So how many model types do we have? We have analogous models, which is 3D, three-dimensional models. Those are sculptures, architectural models, sculptures, or whatever. I mean, all these three-dimensional models, three-dimensional representations of the reality, are analogous models. These small trains, toy trains, perhaps, or toy cars you just played with in your childhood, or even perhaps you play now. There are adults very fond of these small trains, these model trains, maquettes. So this is important. There's a whole sector about it. So those are analogous models. Those are the models of a real train, for instance. You have a real train and its copy, its small copy, which goes on a railway, a small stylized railway with electricity or so, and people make sort of models of it and then play with it. All these toys are analogous models. Even the small cars, small trucks are analogous models of the real ones. Here we have a Buddha sculpture, which is an analogous model of real Buddha, if he existed. All right. The second type of models we have are iconic models. Iconic models, 2D, two-dimensional models. Those are pictures of any kind. The word icon, we use it now for these small pictures where we click on and then it makes something in our computer. That's what we call icon now. But icon originally, ikona in Greek, were religious pictures describing especially Christian or even before Christianity. There were the Buddhist pictures or so on. In Islam, they are forbidden, but in other religions, they are icons showing the religious figures, religious saints, religious persons, prophets, gods, whatever is important in that religion. So the painters depicted these figures and made icons. Icon is mainly these religious figures. Now we use iconic models. All the pictures are iconic models. All the architectural drawings, city planners drawings, electronic drawings or whatever, all these are iconic models. When it is 2D, two-dimensional, it is iconic. You see, we took the reality, which is too complex. We just cut away many parts of it, and we are left with a 3D, three-dimensional object representing this very complex reality. But then we cut away one more particularity, one more dimension, and we are left with 2 dimensions, with a picture. This is yet a model of the reality. Now, in mathematics and in economics, and in physics and chemistry either, we don't use these 3-dimensional or 2-dimensional models. Architects, city planners, designers, all these people, they use 3-dimensional, 2-dimensional models, the analogous and iconic models. But what we use in economics and in mathematics, in the other, in physics and chemistry, whatever, we use logical mathematical models where there is no more dimension. Even these 2 dimensions are sort of thrown away. We are left with a simple relationship. E equals mc square. Whose model is it? It is Einstein's model, Einstein's basic model, representing the transformation of mass into energy, energy into mass. E is a capital E represents energy. It is the first letter. It is the head letter, the first letter of the energy. M represents the mass. It is the first letter of mass. C represents the speed of light. Why is it C? I don't know. It has nothing to do with light or speed, but well, perhaps because it's a constant. It's thought to be a constant. So this is the initial of constant. And there is a 2, which is a little bit higher than C, which means square, which means you multiply C with itself. Square means this in mathematics. And there is an equal sign, which means left-hand side is equal to the right-hand side. They say the same thing. They are equivalent. They are equal. You see, we have only letters and signs, nothing else. There is no picture, there is no sculpture, nothing else, but we are left with a relationship. And we show this relationship, which is one of the fundamental relationships of all the universe, the transformation of energy into mass and to mass into energy. And this is a model, this is a mathematical model by Einstein. So it is represented with letters and numbers, small symbols, nothing else. So we will deal with this type of model, the logical mathematical models, you see? All right. So let's speculate a little bit about science, the thing we are doing now, we are learning. What is science? What does the scientist? So, well, the scientist or the science starts by observing something. The scientist observes an incident, a question or a problem. Really, it observes an incident. We can say, for instance, well, about the nature or the society, of course. You can observe some natural event or a social event, or say a natural incident or a social incident. And then you try to start reflecting upon it. Let's say, for instance, our far relatives, the cavemen and cavewomen, before history. So they used to live in caves, and well, they had perhaps discovered the fire. They know perhaps what is fire, perhaps not. But then they observe some lightning, or as a thunder, the thunder and the lightning. So, well, there can be two explanations about it. Two people observe a lightning and rain, for instance. Heavy rain and lightning. Then the one person, one of these cavemen, can say, well, this is the anger of the gods. We have made something wrong. We have made some, well, some wrongdoing, something wrong, something bad, and the gods are punishing it with this lightning, for instance. This is an explanation, like it or not. The other one, which doesn't see like this, may say, well, it seems that these things have something to do with the clouds. A kind of light is going between clouds or from clouds to the earth. So perhaps there is something else. It is not gods, but there is a kind of force or something between. There is something happening between the cloud and the earth, or between the clouds. He might speculate. He might say. Well, both are good explanations. If we don't have any other knowledge, both are explanations, like it or not. So, what did they do? They built a model about this incident, question, or problem. Everyone his own model. They observed the incident, the lightning, and they built a model about this incident, which intrigues them. They should explain somehow this lightning, which is a special, which is perhaps as well. They might consider it as something perilous, something dangerous as well, something scary. So they have to explain it. All right. One says, this is the anger of gods. They punish us because of our wrongdoings. All right. The other one says, no, this is not gods, it's something else between clouds, or between cloud and the earth. All right, this is also an explanation. So what should we do? They have invented models. One is a model of gods, the other one is a model of clouds and earth, and they have invented an explanation, hypothesis. A scientific explanation is an hypothesis. It's a conjecture. They think so, they believe so. It's a conjecture. They think, one thinks it is gods, the other one thinks it is clouds. Clouds and some interaction between clouds, for instance. So, what should they do? They should test this explanation. Once they observed the incident, they built a model, and they invented an explanation and a hypothesis based on this model. They have to test this explanation with real facts, which means observations, data. I call this comparing or tapping eggs. So you have several explanations. You tap them against each other like eggs. We tap them against the reality, against real data, real observations, and see which ones break, which ones doesn't, or don't break. So this is testing phases, the phase of testing, tests. So how do we test this hypothesis? What we can do to test the hypothesis of God's punishing man, God's punishing human being because of wrongdoings, and sending lightning, we can test it by making some wrongdoings according to our religion, for instance, and observe whether after each wrongdoing comes a lightning. If it comes, then it's very probable that the gods are punishing us for our wrongdoing. But if after our wrongdoing the lightning doesn't come, then this egg is broken. It means this conjecture, this explanation, this hypothesis is falsified. It is not accepted. It is falsified. Because if God's punished us because of our wrongdoings with lightning, then every time we made a bad thing, a wrongdoing, then a lightning should come. If it doesn't come, then it means there is something else. And the other one says, for instance, well, every time there are more clouds and rain, then there is lightning. So there should be a force between these things. And of course, this one would not be falsified. Whenever there is a storm, whenever there is rain, there will be some lightnings, some thunders, and this will not be falsified. This will not be verified either, but this will not be falsified. At each event, perhaps locally, it will be verified, but it will not be falsified. And so we can start speculating, and we can invent electricity with this way of thinking. You see? So this is the scientific way of thinking. If the egg breaks, so the scientist invents a new model or explanation. So if the hypothesis is falsified, it is not supported by the data, then the scientist invents a new model or explanation. You see? All right. Well, since I am alone at this lecture, I don't stop. I will finish my whole presentation. I have 28 slides in this first introduction. I will finish them all, and you will just watch afterwards. If you come to our next session, then we can also discuss together. But as I said, you can always reach me through my phone or the WhatsApp, Telegram, and you can watch my my lectures at my YouTube channel. So just profit from these occasions, from these sources. But you can reach me whenever you wish. All right. So here we have a question, what is the difference between a sorcerer, a shaman, and a scientist? Because what we have done up to now looks like more or less like the activity of a sorcerer, of a shaman in the primitive societies. Once upon a time, in Turkic societies, there were shamans as well. Even today, there are some shamans in Africa, in Asia, in wherever, in the indigenous people in America, there are shamans. So what is the difference of a scientist and of a sorcerer or shaman? There should be some difference. Well, there is not much difference indeed, but an essential one. There is an essential one. All that a scientist says and does must be, 1, recordable. You should be able to record any of these things or of these happenings, these events, this data, whatever. 2, it should be transferable. Second, it should be recordable and transferable. If I do something, if I claim it is scientific, then I should be able to transfer it by writing, by saying, by describing, by some experiment, whatever, to you, to another person. It should be transferable. It should not stay in me. Well, I am the shaman, I have contacts with gods or with powers of nature, and nobody else does. Well, this is not scientific. If I am a scientist, I record anything I do, anything I observe, anything I come across, and I invent, and then I should be able to transfer all these to you, to another person, to another scientist, to whomever wants to learn about it. 3, it should be repeatable under the same conditions, under the same circumstances. If it is an experiment, if I repeat the conditions of the experiment, I should reach the same conclusions. If under the same conditions, if I reach once another conclusion, another day another conclusion, this is not scientific. Under the same conditions, if the conditions are all the same, then this experiment should give the same result. Otherwise, it is not scientific. You see? And most important of all, it should be falsifiable. It should be able to be refuted, falsified. Dogmas have no place in science. Science doesn't deal with dogmas. It is outside the science. In science, there is no dogma. There can't be any dogma in the science. In dogmas, sort of fixed ideas, dogmas, have no place in science. Every scientific proposition should be falsifiable. Something which is not falsifiable, which cannot be refuted, is a dogma. And those have no place in science. Anything I say, if I'm a scientist, if I make science, it should be falsifiable, it should be able to be refuted. Comparing with the real data, of course. You see, this is very important. All right, so now that we have an idea about what we are doing here, or what we will be doing, well, we will deal with mathematics, of course, but all these mathematics will serve to make science and to deal with real-world situations. So this is important to know what we are doing. Our textbook is Alpha Chang's and Kevin Wainwright's Fundamental Methods of Mathematical Economics. The newer sort of publishing is better. I use the fourth publishing. It's McGraw-Hill, but you don't have to buy it. I will share with you the English PDF of this book and also a solution book, so you will have in hand in PDF. Well, you have the Turkish books. Perhaps you have already this book somehow from, I don't know, if you have already studied a little bit in the political science faculty, for instance, before, then you might have bought this book. You can use it. We will use in English, of course, but even the Turkish version would do. And my lectures are based on this book. On our page, the web page, the Ankuzev page, I observed that there are some books and some materials remaining from Türkmen Göksel Hoca, our dear Professor Türkmen Göksel. We can also use them, but they are not in the order I will follow. Please follow my syllabus, but you can use also these old materials, the materials remaining from Professor Göksel, for I mean the same sort, of course, following the syllabus, following the order of the subjects. Then you can also use this material as well. And I will try to give some hints, some references to this material as well, since it is already on our web page, on the Ankuzev's page of this course. I will not erase it, but our main textbook will be Alpha Chang and Kevin Wainwright's Fundamental Methods of Mathematical Economics. All right. So, what is it about this chapter 1? The chapter 1 of this book is the nature of mathematical economics. You will just read by yourself, but I will give a small explanation. It's just 2-3 pages, not much, and it is very understandable, but I will give you the main messages of this chapter, and it has 2 subheadings. So I will just give an idea about it, and you will read the rest from this book. 1.1 is mathematical versus non-mathematical verbal economics. Well, economics has not been a mathematical discipline since antiquity. You find economics texts in Socrates, in Plato, in Aristotle, in many people, in many antique philosophers wrote about economics as well. And the word economics comes from the ancient Greek oikonomia. Eco, like in ecology today, ecology, economics, it comes from the same root, eco or öko. In Greek, it means house. Ecology today is the science of the house of the universe, of the nature we are living in. And economics, nomos are rules. Ökonomos, economics, means rules of administering a house, because economics started from the administration of big houses, big mansions in antiquity. The word economics itself comes from the ancient Greek. You have the writings of, as I said, Aristotle, Plato, Socrates, called oikonomos, oikonomia, etc. So the word comes from antique Greek. You see? And up to perhaps, well, 19th century, and even the, I would say, even the half of the 19th century after Christ, the economics was a verbal discipline. People didn't use mathematics for analyzing economic problems, but they used the text, the main language, the everyday language of people. Ibn Khaldun, for instance, in Middle Ages, he wrote in 13th century, perhaps 12th, or I'm not sure, 11th. I don't know exactly when he lived, and he wrote his Mukaddima, the introduction. In fact, Mukaddima means introduction, because his aim was writing a history book, but in his introduction to this history book, Mukaddima, he made a sort of a door or a big treatise of sociology and economics. So he wrote economics without mathematics. This was a verbal economics, you see. And up to the half of the 19th century, the economics was mainly a verbal discipline. Adam Smith, Wealth of Nations, his treatise, his big book, well, mostly it is verbal. Yet it is one of the most influential, it is the basic, one of the most basic, most sort of starting funding books of the economics, of the modern economics. You see, so economics is not mathematics. Economics uses, and all the other sciences, social or natural sciences, use mathematics as a tool, not as a name by itself. Economics deals with the with the wealth and wealth interactions in societies. It's a social science. It's a social science which uses mathematics, and it is not mathematics by itself. So there is the verbal economics and there is mathematical economics, which is economics discussed by mathematical models. So we use mathematics as a tool, not as a name, as a means, as an objective by itself, but as a means, as a tool. And there is also at 1-2, there is mathematical economics versus econometrics. There, econometrics, in fact, is statistics, which derives also from mathematics. Statistics is a branch of mathematics. It's a kind of discipline derived or developed over mathematics. And econometrics is the study of the economic problems, economic hypotheses with statistics. So it is mathematical as well, but it's not mathematical economics. Econometrics or sociometrics or psychometrics, all these sciences have metrics, which means measuring. You should measure, you should use mathematical tools to test the hypothesis of your science. Econometrics is the building and testing of hypothesis, economic hypothesis, by statistical means, statistical methods. So this is econometrics. And the rest you will read by yourself. All right. Let's see. Yes, at chapter 2, we come to the economic models. Chapter 1 is this one. And the main idea is this. You will read some 2-3 pages, and this is the elaboration of these two main ideas. What is mathematical economics and what is econometrics? Chapter 2 is about economic models. So we have already an idea about models from this model of tree, so to say, the pine tree model. But what are economic models then? Those are simplified skeletons or caricatures of the complex economic reality. As this pine tree picture was a skeleton or caricature of the complex pine tree, economic models, they are simplified skeletons or caricatures of the complex economic reality. You see, it's the same thing but with economics. Those are also theoretical frameworks and not necessarily mathematical. You see, they are not necessarily mathematical. They can be taught, described with verbal or other means, languages. You see, we can use many languages. Mathematics is a language as well. It is the most economic language. In mathematics, you can say many things with very few words, very few symbols. But you can use also everyday language, Turkish, English, whatever language you know, to explain economic realities, economic models, economic hypotheses, whatever. You can make economics without any mathematical sign at all, just by plain language, human language. Or you can use mathematics to describe all these things in less words, less symbols. For instance, there is in the Karl Marx Capital, the second tome of the Capital, second volume of the Capital, there is a accumulation model. Today we would say a growth model. He said accumulation model, where he described the model in about 10 pages. Because at his time, mathematics was not so developed, or the mathematical tools were not so developed to describe perhaps these models, his model. But then afterwards, in 20th century, a mathematician and economist called Morishima, Japanese, he described the same model with two equations, 10 pages against two equations. This is the power of mathematics. It says the same thing. It doesn't say anything else, anything more, anything less. It says the same thing. It says what Marx said. But Morishima expressed the same idea with two equations instead of 10 pages. You see? This is mathematics. All right. So they are theoretical frameworks. Economic models are theoretical frameworks and not necessarily mathematical. They can be told, described with verbal or other means, other languages. And don't forget, mathematics is a language as well. Elements of a mathematical model. Are toys. In fact, we will play with these toys. The whole thing is a play, and we will play with these toys. The main toys are variables. They are not pronounced variables, as somebody pronounces, but they are pronounced variables. To vary is the verb, to change, it means to change, and variable is something which is changeable. Variable, changeable, it can be changed. What are these? These are small cars, small wagons, small recipients. They are empty. Some empty recipients with some wheels. They can be moved, they can be ordered, and you can put anything you wish in them. We call them in mathematics X, Y, Z. We call them with some letters. You can, if you are a physicist, for instance, you can put in them some forces, some resistance, electricity, whatever, these things, for instance. If you are a chemist, you can put oxygen, hydrogen, nitrogen, whatever, all these elements, for instance, in variables. And if you are an economist, or somebody who deals with economics, then you can put in it cost, profit, price, quantity, these things, for instance. And those are, as I said, those are recipients, empty recipients. You can put whatever you wish in them, and then you can tie them with some operations like plus, minus, division, multiplication, or some equal signs or whatever. If you have these operations, you can tie them together and make a sort of a train out of it. You see? And if you make it in a function is the locomotive of the train, so you make a whole train and it moves. I don't know whether it moves. Sometimes it moves, this thing. Anyway, so you see, a function is a train, or an equation rather is a train, where there is the function and the variables and some operations tying them. So the whole thing is an equation. The train is an equation. The function is the locomotive, and variables are the wagons of the train. And they are tied together with some operations, and they describe something. You see? A phenomenon. All right. So these variables are also classified. We have variables, constants, and parameters. What are variables? What are constants? What are parameters? But don't we have something before? I think. Is there some? Let me see. Oh, yeah, no. All right, no problem. So, variables, constant, and parameters. Variables are well, as the name indicates, they are symbols which can take quite various values. Those are empty wagons, as I said, or players in a theater which can take many roles. Economic examples are price, P, price, Q, quantity, R, revenue, C, cost, P, profit. Those are the variables we use, and there are others as well, in economics. There are also Y, national income, C, consumption, X, exports, M, imports, so on. There are many variables. And we usually represent them with with capital letters, sometimes small letters as well. But the initial letter, the first letter, the initial letter of the English expression for this quantity, or for this concept. So you see, P, price, the initial is P, quantity, initial is Q, revenue, initial is R, so on. Profit is P. Why? In order not to mix it, to confound it with price. If price is P, profit it starts with P as well. So we use the Greek P instead of the Latin P. You see, the Roman P, price, the Greek P, pi, is profit. You see. All right. So these variables are also classified into two groups, endogenous variables and exogenous variables. What does it mean? Endogenous, you see, endo is inside, exo outside. Endo, exo. Endo in, exo out. Exo. Endo in, exo out. Genus, genes. What does it mean? We say genealogy, for instance, the science of the how can I say, of the family. Genes. What are genes? Those are small particles, small sort of pieces in a cell, which transfers the knowledge of this creature, of this body, into the cell. So genes. You see, it comes from the birth, from coming into the birth, from coming into the being. So endogenous is living inside, being born inside. Exogenous, being born outside, living outside. The original meaning is this, the etymology. So endogenous variables are variables being the main matter of interest of a model. What we are really interested in, what we are really studying is, those are the variables being the main matter of interest of a model, and whose solution values are found in the model. We find the equilibrium values, the solution values of these endogenous variables in the model itself. Example, the output or supply. It's called also supply, output or supply quantity, QS, quantity supplied, of an agricultural product. Or its quantity demanded, QD, Q sub D, Q sub S, Q sub D. You see, we have Q sub S and Q sub D. Quantity supplied, quantity demanded. And its market price, P. Those can be the endogenous variables of a model. These three variables are sufficient to make a model, as we will see. We have quantity supplied, quantity demanded, and market price. All right. The price of the good, one good model, we will see. And there are also exogenous variables. Those are variables entering the model from outside. They are born outside, they come from outside as data. They are given. Data means given. In fact, it's Latin, and it means datum, data, datum, data, means given, something given from outside, given as some given numbers, data, whose values are given and not sold in the model. You see, they come to the model from outside and they are not sold in the model. Their values are not determined in the model. They come as data. They come as given from outside, and we use them to solve the endogenous variables, the equilibrium values or the solution values of the endogenous variables, the real values, the main value, the main variables of the model. You see, examples of exogenous variables are, well, for instance, the yearly average air temperature at that region, T, and the quantity of rainfall, R. If I'm interested in the quantity supplied, quantity demanded, and the price of an agricultural product, the quantity supplied, which is the output, the production of this wheat, for instance, or corn, it would depend on the yearly average temperature at that region. And the quantity of rainfall, of course, T and R. Those are exogenous variables. I take them from meteorologists. For a meteorologist, those would be endogenous variables. For the economist, they would be exogenous variables. I will take these values from meteorologists and use them in my model as exogenous variables to solve the market price, the equilibrium price of the wheat or corn, for instance, as the solution of the equilibrium value of an endogenous variable, you see, or quantity supplied or quantity demanded. All. So, also these variables, they take also other names and they change a little bit the nature. Constants are symbols which can take only one value, as the name indicates. It's like an actor staying motionless at the same place on the stage during a theater play. You see, in a theater play, well, let's say I don't have enough money. I can't put a tree on the stage. I tell one of my actors, one of my players, to act like a tree, to stay somewhere on the stage during the whole play like a tree, and he stays over there like a tree. He just simulates a tree. So this is a constant. It takes just one value during the whole model, during the whole analysis. As an actor staying motionless at the same place on the stage during a theater play, actually, and exactly. Our examples are, for instance, natural constants. Number pi, which is 3,14159, etc. It just goes on like this without repeating itself. The famous number pi. It has even a day, the pi day in a year. It is, I guess we passed it. It was in December or November, somewhere over there. Another number like this is the Euler number. Euler, the German mathematician, he is the father of this number. That's why it is called E with the initial of his name, Euler. And it is 2,71 or 828, etc. And it doesn't repeat itself either. It goes on like this. Those are two natural constants. You know pi, when you divide a sort of a circumference, a circle, by its radius, you obtain this number. The Euler number is a little more complicated. You find it, I mean, in many places in nature, in some, well, in some seashells, or in plants, or in many things, but it has an economic origin. very interestingly. And I will tell you when the time comes. I guess I will try to tell you where this number comes from. Not now, but later, later on towards the perhaps the end of this course. All right, so these are constants. There are also parameters. Parameters are variable constants. Funny, isn't it? I mean, there are variables, there are constant, and there are variable constants, parameters. That's to say, they can take more than one, but a few values. But they can't take so many and even infinitely many values like variables. Variables can take many values or infinitely many values, but parameters can take a few values. Like for instance, this one, I minus 1, 0, 1. This parameter takes minus 1, 0, 1. This is a parameter very much used in electronics. When the current doesn't pass, it is 0. When it is a positive pole, positive current, it is 1. When it is negative current, it is minus 1. This is a way to represent an alternative but square wave. It is called a square wave in electronics. You can use this parameter to represent a square wave in electronics, for instance, or other parameters. We will use many parameters as well. But those are variables taking just a few values. They are not constants. They don't take just one value. They take more than one value. But they don't take as many values as the variables. They take a few values. Those are parameters. All right. So equations. We have also equations and identities. We have mainly three types of equations. And what they show, these equations, they show the relations between variables. They model relations. And there are three types of equations. The first one is definitional equations. And it is shown by these three equal. Normally, equality is shown by these two equal, the equal with two sort of two lines. But when you make the equal with three lines, like this, it means an identity or equivalence, and they show the definitional equations. Those are definitions or equations which are always equal. You cannot make them unequal. So you cannot make an inequality out of it. They are always equal. They establish an identity or equivalence between two expressions having the same meaning, indeed. Definitional equations. The example, pi, in this case, profit, total profit, is identical to, it is equal but identical. It is, or equivalent to or identical to. These three equal is called, or it is read, it's pronounced identical to or equivalent to. So pi is equivalent to TR minus TC. Total profit is equivalent to total revenue minus total cost. Here is an economic identity. It's a definitional equation, which means we put just a kind of a sign. We say the pi profit means total revenue minus total cost. We define the profit, so they are definitional equations. They can't be unequal. You can't destroy this equality, because that's us, that's we who give the name of profit to total revenue minus total cost. It is just a name. We put the name on it. Total profit minus total revenue minus total cost means profit. So P is identical or equivalent to TR minus TC. The second type of equations are behavioral equations, and they are shown by two equal, the usual equal sign. They model the behavior of the reaction of a variable to a change in other variables, and they model the behavior of all living or unliving beings. You can model the behavior of living or unliving beings. What is unliving beings behaving? For instance, atoms. or molecules. Atoms or molecules are not living. They are not animals. They move. They move even very fast, all these atoms and molecules, and you can model their behavior. Physicists do it. We don't do it, but physicists do it. So you can model the behavior of or structural engineers, civil engineers. What do? They model the behavior of the structures of the houses, of the buildings. The geologists model the behavior of the earth, of the layers of the earth, for instance. So you see, you can model the behavior of anything, be it living or unliving. So the example, an economic example, is C equals. You see, I pronounce this equal. The other one is equivalent or identical to. This one is C is equal to. You see the difference. C is equal to 75 plus 10Q. C represents cost, Q quantity produced of something. The cost of something, of this good, is equal to 75, which is the fixed cost, plus 10Q, which is the variable cost. It varies with the quantity produced. Each unit of quantity produced adds $10, for instance, to your costs. So 10 times Q is your variable cost, plus you have to make a $75 primary cost, a fixed cost, in order to start your production. Even before producing 1 unit of Q, you have to spend $75 to establish this machine or whatever, the production line, this factory or whatever, this shop even. So this is the fixed cost. 75 is the fixed cost. 10Q, 10 times Q, is the variable cost. And when you sum them up, you obtain the total cost. Total cost is equal to fixed cost plus variable cost. And in numbers, it can be something like this. C is equal to 75 plus 10Q. This is a function showing a cost. This is a cost function, a total cost function. C is cost, Q is quantity produced. You see? We started modeling, making some economic models. And the third type of equations are equilibrium or disequilibrium conditions. They can also show disequilibrium in dynamic models. In static models, they will show equilibrium conditions. Mostly we will deal with equilibrium conditions, but just have in mind that they can also show disequilibrium. So they are equalities, less than, greater than, less than or equal, greater than or equal. Some sign has changed here, but I will correct it. It is correct in the presentation, in the PowerPoint, but passing to here at this environment, it changed. No matter. Those are signs like this. I mean, equal, less than, greater than, less than or equal, greater than, equal to. And these are the equations closing, which means tying together the model, which are the preconditions of attaining the equilibrium, obtaining the equilibrium, or getting into motion if it is this equilibrium. You can also model a motion with these, but this is a more elaborate, more advanced phase. We will deal with equilibrium conditions. Those are the preconditions of attaining the equilibrium of the model and of the behaviors in it. Exactly. An example is QD equals QS. Quantity demanded is equal to quantity supplied of a good. This is called demand-supply equality. The famous arz-talep kanunu in Turkish. Demand-supply law, or demand-supply equality, or supply-demand equality, whatever you wish. So QD equals QS. Quantity demanded is equal to quantity supplied. What you produce or what you sell, this quantity supplied, is equal to what people buys, demands. If you obtain this equality, the market is in equilibrium, for instance. Or S equals I, saving investment equality. What we don't produce, we produce something, we earn something, we make some earnings, for instance, and what we don't consume, we save it to the future. We make some savings. If you put your savings under your pillow, they don't serve to anything. If you make a business, if you build a business with them, or if you invest in actions, for instance, then they produce something. So savings are transformed into investments. And there is a huge debate in economics about whether these savings are transformed, are equal directly, they are transformed to investment or not. If not, you should give some incentives. You should do something to transform them into investments. Otherwise, your savings would be hoarding, which is, what you put under your pillow, or in your cash vault, whatever in your vault, doesn't serve in economics. It doesn't produce anything. So they should be transformed into production means, into means of production. Then they become investment. You see, so savings are equal to investment or not is a very vivid debate in economics, and this is saving investment equality. Or another one, marginal cost equals marginal revenue equality. We will see that this is a basic equilibrium condition, especially in terms of derivatives. Marginal cost and marginal revenue are some derivatives, and when they are equal, we obtain an optimum situation. Marginal cost equals marginal revenue. And this is also an economic equality, economic equilibrium condition. You see, equilibrium comes from equi, equal, and libra, which is the balance. Equilibrium, equilibra, from Latin, it is the equal balance. As the two sides of the balance are balanced, they are in the same position. So equilibrium is a left-hand side and right-hand side are balanced. This means this from the physical balance it comes. You see? All right. So today we finished our lecture. Here is, I hope everything is recorded. I don't see any, yes, in the, everything is recorded. So just watch it and read the PowerPoint presentation of this, which I presented now, and then come with questions. You can always call me up, and if you also send me your phone numbers, we can make a small WhatsApp group and discuss all these things over there as well. And you are welcome to participate in my next lecture next Monday at 2:30 in the afternoon. That means 14:30. Thanks for today, and see you next week. And I hope to hear from you before next week anyway. Have a nice day, have a nice week, and have a nice term. Thank you very much. Bye-bye.